All right, that's Mr. McMurray back again. And just to remind you, we've been talking about liquids, which are one type of fluid, but the other type of fluid is a gas. And a gas is basically, if you want to think about it, as a thinned out or watered down, no pun intended, watered down liquid. All right. If you start with solid, the atoms are packed closely together. They can barely vibrate in place. But once they break loose in a liquid, they can slide around each other, but they can't leave the liquid. And finally, if they get hot enough, they break loose completely in a gas. In a gas, the molecules are constantly moving around and spreading apart and so forth. So it's just kind of going from a solid to a liquid. They got a lot more movement. And when you go to gas, they're much farther spread out, and they're just constantly moving, and they're very, very, very far apart. That's why it's a lot easier to walk through air than it would be to walk through water. Okay, which is possible, but you get more exercise walking through water, so they have water aerobics as opposed to air aerobics. And if you move through air, you can still feel the air as you move through it, so it's there, but it doesn't have nearly as much resistance because the atoms are much spread farther apart and everything. But basically, that's why gases and liquids are both considered fluids. Okay, in the gas, they're just much farther apart. They can move around a lot easier. But both a liquid and a gas expand to fill or to take the shape of their container. If you pour a liquid into a jar, then it takes the shape of the container, as does a gas. However, a gas doesn't settle at the bottom. It will spread throughout the container and fill up the container. You can't have half a jar full of air unless you have liquid or solid in there, because if there's just space in there, then the gas will spread to fill up the container. Okay. Now, when they fill up the container, these, for example, here are just a cross section of some tires. Okay. You have these atoms inside the tire, and they are constantly moving, and as they move, they're going to hit the walls. Okay. And when they hit the walls, they exert a force. Okay. So that basically is pressure. So air pressure is when the molecules move and hit the walls of its container, and it exerts pressure on it. Okay, so that's what we talk about air pressure. Talking about the air pressure in your tires. Talking about how many molecules in there, how fast are they moving, and how often do they hit the walls. Okay. Now, things can change. If you have a low tire, it's going flat, it has a low air pressure. Why? Because there's less dense, less molecules, therefore less molecules hitting the wall, and therefore they're exerting less force on the area of the wall and the inside of the tire, and therefore you have a low pressure. Since you don't have much force, then you have a low pressure. So basically, the density of the gas, if you were to increase the density and put more molecules in there, they're going to be hitting the walls faster, harder, more often, and because it's much more crowded in there, so they're going to be hitting the walls much more often. That means you increase force on it, and therefore we say the tire has a higher air pressure. When you air up the tire, that's what you're doing. You basically put more and more of these air molecules in there, and they keep hitting the walls more and more often because there's more of them, and therefore you have a bigger force, and therefore we say that air pressure goes up. Or you have a pressure of, for example, car tires very often 30 to 35 pounds per square inch. Okay, and that has with the force that they exert on the side of the tire. Okay, now it can also be affected by the volume. Okay, what if we change the amount of volume that we have? Well, for example, this is like a piston, a chamber, like it could be in your motor. Okay, if they have this much volume, then they're going to bounce around, hit the walls, and exert a certain pressure. But if you squeeze them into a smaller amount of space, even though you have the same number of atoms, now they're going to hit the walls a lot quicker because there's not as much room to move around in, and they're going to hit the wall more often, causing more force, which has a higher pressure. So this one is going to have a higher pressure than this one, even though there's the same amount of gas in there, because we have reduced the volume, so that's going to increase the pressure. Right. And so basically, if you increase the volume, you give them more space, you're going to decrease the pressure. Okay. If you decrease the volume, you're going to increase the pressure. So basically, pressure and volume are going to do the opposite of each other. Okay. If you increase the density, either by shoving them closer together, which makes it more dense, or by adding more air, which increases the density in the tire, of the gas in there, then it's going to increase the pressure. If you decrease the density, give them more space to take up, then you're going to have lower air pressure. All right, a scientist named, James Robert Boyle, in the 1600s was studying this relationship, and so he had the honor of having it named in honor of him. And so it is called Boyle's Law, okay? And Boyle's Law basically boils down to this, pardon the pun again, but he said if we take the pressure times the volume of the original gas or fluid, and then we change either the volume or the pressure, the total of the sum of these two multiplied together, the pressure and volume, should equal to the pressure and volume multiplied together here. Okay, and so in this case up here, the pressure is fairly low and the volume is fairly high. Okay, when we squeeze it down, now the volume is low, but we've increased the pressure. So since originally we had a big volume and relatively small pressure, now we have a high pressure but a relatively small volume. And when you multiply these two together, you're going to get about the same answer on each side. Okay, and so they're going to be equal to each other. And so if we have a gas or a fluid at a certain volume and we want to change the volume, we can use this formula to predict. If we know the new volume, we're going to say make it half as much volume, we can predict how much pressure that will have, or vice versa. If we're going to change the amount of pressure, we can, assuming this is free to move, we can estimate how much it will push it up and what the new volume will be. So his law is useful for that. So we have the pressure times the volume before, think of this as the before side, okay, and then we change something, and now pressure and volume on the other side is same. Now, just for the record, this is if you keep temperature the same, then Boyle's law is true, but technically it's only true if you keep temperature. Temperature can also increase that. If we increase the temperature, these atoms will move faster, which will cause them to hit it more often, and it will do what to your force that they hit? It's going to increase the force, which is going to increase the pressure. If we increase them, and if this piston here is free to move, it may push open and increase the volume. So temperature can also affect that, but we're not going to worry about that for right now. If we just change either pressure or volume, then we can calculate what the new pressure and the new volume will be. Okay. So for example, if I double the volume, so it was whatever, and I double it twice as big, then I know that the pressure over here is going to have to be half as much. Okay, because otherwise this is twice as big, so I got to multiply by a number that's half as much, so that I get the same on both sides. So that's assuming that temperature is held constant. Now, just for your information, though we won't do any problems with it, there is a formula which is still sets them equal to each other, but temperature goes on the bottom, and both of the sides have to be divided by the first temperature and the second temperature. So in real life, you would have all three of these, but this is not real life, this is physical science, and we're only going to worry about this part. Assuming the temperature is the same, the pressure, the original pressure times the original volume is going to be equal to the after pressure and the after volume after you change something. Now, just as we talked about with fluid or liquids, the amount of pressure you feel depends on how much of the water is above you. The same thing is true of air pressure. We don't think about air pressure because we are constantly underneath the air and feeling the air pressure. Okay? But same thing is true. We live literally in an ocean of air. All right? And it's above us and it's pushing down on us, its weight. For example, 1 cubic meter, that'd be 1 meter by 1 meter by 1 meter, has a mass of 1.2 kilograms. Now, the atmosphere reaches up for miles above us, and so all the air above us is pushing down on us. Now, as you go farther up, that 1 cubic meter of air that weighs 1.2 kilograms, if you get about 5 miles up in the air, 4.5 to 5 miles, it only has a mass of 0.4 kilograms because the atmosphere gets thinner as you go up. There's less molecules in there, kind of like this, and therefore it has less mass. Okay, the farther you are closer to the ground, there are more atoms and it's more dense, and so it has a higher mass. But all that way up above us, you could just draw a little column above your head all the way up to the top of the atmosphere. All of that is weighing down on you, and that's what air pressure is. Okay, air pressure is measuring that column of air. It's weighing down on top of you. All right. Now, to measure air pressure, we use barometers, or sometimes you'll hear anemometers. But the original barometer was basically this. It's a long test tube type structure, but it's about 36 inches long. Okay, it's a very long test tube, and it was filled with mercury. And then they had a little bowl part down here at the bottom. It was filled with mercury, and they would flip it over upside down. This was completely full of mercury. But mercury is very, very heavy. Okay, and so even though there's no way anything can get in here, the weight of the mercury would pull down. Okay, and they would measure that. So this would be like 760 millimeters of mercury. Okay, and that's how high this is. And this up here would just be a vacuum, nothing in there. Okay, so just the weight of it would pull it down and create a vacuum up here. Now, if the air pressure gets higher and it's pushing on this bowl down here full of mercury, it pushes on the mercury and it will push the mercury up. And so we say the mercury is rising, or the pressure is rising. Okay, because there's more air pressure, it pushes on this mercury and pushes the mercury up the tube. All right, and that's usually associated with warmer, hot, dry weather. On the other hand, if there's less air pressure, then it doesn't push as hard on this, and it allows some of this mercury to fall back into the bowl, and it goes down. And so we say we have a falling barometer, or we have falling air pressure, and that usually is more likely to be associated with a change in the weather, such as rain and stormier weather like that. And so that's what we're talking about when we talk about the barometer rising or falling. It's literally this tube of mercury. You could do the same thing with the water one. Unfortunately, the tube would have to be about 30 feet tall, if I remember right. And because water does not weigh enough to pull down like this, and therefore be moved up and down like the mercury is. Mercury works because it's so heavy. Okay. So basically, that's how the barometers work. Now, the units of air pressure, there are several different units that are used to measure it. Why exactly are there so many different units? I don't know all the answers to that. Part of it is because you have people in chemistry and people in physics and people in different branches and weather that were all developing units, and so they kind of came up probably with their own units, and so they've tried to mix those together. But some that you may hear, there's PA, which is for, and it shouldn't be underlined necessarily, but that's called pascals, and that's the official unit of air pressure, named for the man who invented the idea. Pascals, so you may hear that. Now, 1 Pascal, okay, so 1 PA is equal to the pressure that you would feel basically if you put a $1 bill, okay, in your hand. So that's a very small amount. So usually we talk about kilopascals because that's just too small. Okay, if you have 101.3 kilopascals, all right, that is equal to a unit called 1 atmosphere. Okay, and 1 atmosphere is the air pressure at sea level. All right, but you may also see, like we already talked about with the barometer, you may also see a measurement of millimeters of mercury. That's talking about how many millimeters tall is this column of mercury in the tube. Okay, so you may hear that. And there's another one called millibars. Okay, and so you may hear all of these units used, just so you're familiar with those, but they all are ways of measuring air pressure. Like I said, it's partly because some are done in chemistry and some in physics and so forth. All right, so that pretty much finishes that section. We're going to come back and talk about Pascal's principle and also about Bernoulli's principle, and then we'll be finished with fluids. Lots of good stuff on fluids. See you next time.